Hey there. You ever just look around at everything and wonder how it all works? I mean, from the phone you're holding to the stars way out in space, it all seems to follow a certain set of rules. Well, today, we're basically going to crack open the user's guide to the universe itself and try to figure out what those rules are.
So let's start with that big question. What are the rules of the universe? Is there some kind of grand instruction manual floating around out there? That one simple question is really the engine behind one of the greatest human adventures ever, the quest to write that how-to guide ourselves.
And you guessed it, that quest has a name. Physics. The best way to think about it is like the ultimate detective story. The entire universe is the crime scene, and the mystery you're trying to solve is uncovering its most fundamental laws. And to do that, you need a method.
And our method for this whole investigation is science. Now, science isn't just a big book of facts. It's an action. It's a process. It's all about being curious, poking around, trying things out, and then seeing if you can predict what's going to happen next. It's really our organized way of asking the universe questions.
So, physics is the part of science that asks the biggest, most fundamental questions. The word itself actually comes from the Greek word for nature. What physics tries to do is drill all the way down to find the most basic, simple laws that govern everything, and then see how those few rules build up to create all the amazing, complex stuff we see around us.
And when I say all the stuff around us, I really mean it. The scope of what physics covers is, well, it's absolutely mind-boggling. It goes from the unbelievably huge to the unimaginably tiny.
And here's where it gets really cool. On one side, you have the macroscopic world. The big stuff we can see, like planets, stars, and the grand cosmic dance of galaxies. But on the other side, you have the microscopic world, the invisible realm of atoms and the tiny particles that make up, well, everything. And the most incredible part? The same basic set of rules governs both of them.
But look, this isn't all just abstract cosmic theory. Understanding these rules is what lets us build our world. That journey, from discovering a physical law to putting that knowledge into the technology in your pocket, that is one of the most powerful stories in human history.
Just think about it for a second. The steam engine that powered the Industrial Revolution, that's the laws of thermodynamics in action. The computer you're using right now, that works because of digital logic, which is all about controlling the flow of electrons, a concept straight out of electromagnetism. Nuclear power is from understanding atomic fission, and rockets launch into space because we figured out Newton's laws of motion. Physics isn't just in a book. It's literally the blueprint for our entire modern world.
Okay, so if physics is the study of the rules, what are the rules? You'd probably think the list would be impossibly long and complicated, right? Well, here's maybe the most incredible part of this whole thing. It turns out the universe's entire instruction manual is shockingly short.
That's it. Just 4. Every single thing that happens, every push, every pull, every explosion, every chemical reaction in your body, everything that has ever happened or ever will happen is just one of those 4 fundamental forces doing its thing. It's such a simple and beautiful idea.
And this hunt for simple, powerful rules was the life's work of giants like Albert Einstein. He dedicated so much of his life to understanding these forces, especially gravity, and he even dreamed of one day uniting them all into a single master theory.
So, who are the big 4? All right, first up, we've got the gravitational force. This is the attraction between anything that has mass. It's what keeps the whole cosmos, planets, stars, galaxies, from just flying apart. Second, the electromagnetic force. This one governs electricity, magnetism, and light, and it's the force that holds your atoms together. Third is the strong nuclear force. Think of it as a kind of cosmic superglue that holds the nucleus of every atom together. And finally, number 4, the weak nuclear force, which is responsible for things like radioactive decay.
But here's the thing. These forces are not created equal, not even close. If we were to look at their relative strengths, and let's say we give gravity a strength value of just 1, the electromagnetic force is a mind-blowing 10 to the power of 36 times stronger. And the strong force? That's about 100 times stronger than that. It just goes to show you how unbelievably weak gravity actually is compared to everything else.
And think about what that means in the real world. This quote here puts it perfectly. When you just hold a book in your hand, the electromagnetic forces between the atoms in your hand are easily winning a cosmic tug-of-war against the gravitational pull of the entire planet Earth. That is just an insane amount of power.
And all these forces are playing out on a stage that's made of these tiny building blocks. The brilliant physicist Richard Feynman once said that if you could only pass down one single piece of scientific knowledge to the next generation, it should be this: everything is made of atoms. And these 4 forces are what tell all those atoms how to act.
Okay, so we found the 4 rules that run the universe. Great. Case closed, right? Well, not exactly. See, one of the most important things to get about science is that the rule book is written in pencil, not permanent marker.
This is probably the most crucial idea in the entire scientific method. There is no final theory. There's no last word. As our tools get better and our observations get more precise, our theories have to adapt to fit the new facts. If a theory doesn't match the evidence, it's the theory that's wrong, not the evidence. End of story.
And this little timeline is a perfect example from history. Copernicus came up with this brilliant idea. Planets orbit the sun in perfect circles. And for its time, it was a huge leap forward. But then, along came Tycho Brahe, who collected the best, most precise data ever on how the planets actually move. And when Johannes Kepler dug into that data, he realized the circles didn't fit. The evidence clearly showed the orbits were actually ellipses. So a good theory got replaced by an even better one, all because it matched reality more closely.
But are there any rules that seem truly unbreakable? Well, yeah, it seems so. The most fundamental, rock-solid principles we've ever found are what we call conservation laws. These laws basically say that in a closed system, certain things can't just be created or destroyed. They can only be changed from one form to another. And these sacred quantities are things like energy, momentum, and electric charge.
And here's where it gets really beautiful and honestly a little deep. Why are these things conserved? It turns out it's because the universe has certain fundamental symmetries. For instance, the law of conservation of energy exists because the rules of physics are the same today as they were yesterday and will be tomorrow. The conservation of momentum exists because the rules are the same here as they are on the other side of the galaxy. It's like the very fabric of reality itself gives rise to these unbreakable laws.
So, there you have it. A quick tour through our physical world, from the tiniest atoms to the biggest galaxies, all run by just 4 forces and a handful of sacred conservation laws. It's the best rule book we've managed to write so far. But if the history of science has taught us anything, it's that there's always another chapter waiting to be written. And the real question is, what discovery is going to be the one that forces us to revise it next?